All right, today we're going to learn about section 2.4, the chain rule, which oddly enough we know about already, at least in part. So this is going to make this a lot easier than normally it would be. All right, number one, find the derivative dy dx. Okay, as we know, there's an invisible 1 in front of the parentheses, so we're going to use power rule. Exponent times coefficient. 8 times 1 is 8. The stuff inside the parentheses, as we know, we copy. Don't do anything to it, just copy it just the way you see it. But the entire quantity goes down by a power. It was 8, now it's 7. Okay, so obviously that's the power rule that we know and love. But here comes the chain rule. Again, happily, this is a review. It should be new, but it's not. Look inside the parentheses or any grouping symbol that you happen to have. Stare at what you see in there and pretend that it's its own original problem. What if the original problem had just been, hey, 5x squared plus 3, what's my derivative? Well, 10x plus 0, of course, because 3 is a constant. All right, well, if the derivative of that red rectangle is 10x, then you need to multiply by that at the end, times 10x. And that has a name, and that is called the chain rule. That's what we're doing. And this would be the final answer if it just didn't look so sloppy. So I'm going to combine the 8 and the 10x, because you don't see it, but really there's a dot here as well. So you can multiply them in any order. So we'll make 80x times the rest of it to the 7th power. And that's the derivative. All right, things are going to get crazy in a hurry now. Y equals sine 6th power 4x plus 9. I have never been a big fan of this abbreviation. Let me rewrite this problem. There, that's the same thing, but it's going to be easier to see. As we know, there's an invisible 1 in front. Let's make it visible. Okay, there it is. And the derivative is going to look like this. Y prime, or dy dx, we'll start with the power rule first. Usually we do. Exponent times coefficient. 6 times 1 is 6. Stuff, still in brackets, still just being copied. Nothing fancy here, I'm just copying off of myself. All right, done copying, brain break over. To the 5th, because the power has to go down by exactly 1. All right, so that is the power rule. But now the chain rule comes in, and there are actually 2 chain rules on this problem. If the chain rule only ever had one part or one link, it wouldn't be called a chain rule. That wouldn't be much of a chain. It would be called like the bracelet rule or the clasp rule or something like that. So it's not surprising you're going to get more than one. So you dig into the inside. You go into the first grouping symbol, which in this case is the bracket, and you say, hey, stuff in the bracket. What if that was the original problem? What if I said, hey, students, welcome to class today. Take the derivative of the sine of 4x plus 9. You'd be like, okay, it's cosine of 4x plus 9. And you're like, okay, good, very good. Derivative of sine is cosine. You are correct. However, if that was the original problem, it would have its very own chain rule. You would dig into the next set of grouping symbols, which in this case is the parentheses. And you would say, does that have a derivative? And you're like, yeah, times 4. I'm like, okay, you need to multiply by that. At this point, you're done. I oftentimes would go too far as a student. I would try to make extra chain rules, and my teacher's like, no, Jeff, stop. There are no more parentheses. There are no more brackets. I guess the next thing that would have a parentheses on it would be this x. It looked kind of weird, but the derivative of x is just times 1, so even if you did put something on the end, it wouldn't change the answer. Speaking of the answer, here it is. You can see I multiplied the 6 and the 4 together. I rewrote the sine part with the 5th power sort of stuck in the middle. Again, I'm not a big fan of that abbreviation, but that's how the textbooks will write it. And there you have it. So 2 chain rules on that problem. Interesting. We're starting to grow this thing. Let's try another. Just as in number 2, I'm going to rewrite this. Notice that the 3 is not being taken to the 4th power. It's not 3 to the 4th. It's not 81. It's just a 3. The tangent is being taken to the 4th power. That's what's happening. Please do not do this. I see this a lot. That's not correct. If you don't have the extra set of parentheses or extra set of brackets around this, then there's only one tangent, and the parentheses, the 2x to the fifth minus 11, that quantity is being taken to the fourth, but there's only one tangent. We have 4 tangents. So again, you have to be careful with how you write things. And a lot of times I have to mark things incorrect, even though I know that you understood, but you wrote an answer that was wrong, or you wrote something on your page that was false. And as a teacher, I can't just look away. I'm doing you a disservice if I do. I'm telling you that things are okay when they're not. So just be careful. All right, let's do the derivative. dy dx, y prime, f prime of x, whatever you want to call it. It's exponent times coefficient, so 4 times 3 is 12. Again, I'm doing the power rule in red here. Stuff inside the parentheses gets copied just as I see it. Nothing fancy here. But it goes down by a power, so not fourth, but third. And now the fun starts. Now you look inside the first set of grouping symbols, the outermost, and you say, hey, tangent of argument. What's the derivative of tangent of argument? Well, it's secant squared of argument. Yeah, that's right. Secant squared of 2x to the fifth minus 11. But then you delve in deeper to the next set of grouping symbols, which is the parentheses, to the argument itself, and you're like, does the argument have a chain rule? And yeah, it does. The derivative of 2x to the fifth minus 11 is 10x to the fourth. So you need to multiply by that as well. We'll combine like terms. I'll get rid of the brackets. We're going to have 120x to the fourth out front. Tangent cubed of 2x to the fifth minus 11 times secant squared of 2x to the fifth minus 11 will be dy dx. All right, and finally number 4, find dy dx. Again, I don't like the way this is written, so I'm going to rewrite it using some clever algebra 1. This is actually 2 to the fourth, which happens to be 16, over 3x minus 1, also to the fourth. Which again, before I do any calculus at all, I'm going to rewrite one more time using some algebra. And I'm going to call this 16 times quantity 3x minus 1 to the negative fourth. All right, now I'm ready to start. As I've been doing, I'll do the first step, the power rule in red. Exponent times coefficient. Negative 4 times 16. That'll be negative 64. Stuff, which is the argument. Just copy it. But take it down by a power. That's negative 5, not negative 3. Go down, not up. Then you have to say, all right, does the quantity inside the parentheses, inside the grouping symbol, have its own derivative? Why, yes, times 3. All right, well, there you go. No more chain rules because there's no more parentheses. Again, the next thing that will get parentheses would be this x, I suppose, and the derivative there is just 1, so you know you can stop. 64 times 3 is going to be negative 192, so the answer is negative 192 over 3x minus 1 to the fifth. You are more than welcome to leave it as negative 192 quantity 3x minus 1 to the negative fifth as well. That's completely fine. I just figured I'd throw a little variety at you. That's it for day 1. I think that's a good introduction. We took what we knew already. We've broadened your horizons a little bit by making the problems a little more involved with extra chains or extra links in the chain. And when we do day 2, we're going to formalize it a little bit more. So I'll see you on the second day soon enough. Until then, peace.